Electromagnetic waves are, in a sense, the culmination of all the things that we have learned about electrical and magnetic phenomena so far. We learned that if we change the linked magnetic flux in a region, an electrical field and an electromotive force is induced in that region. Conversely, when Maxwell presented the paradox of the capacitor, we realized that if the electrical flux linked within a given region is changing with time, a displacement current is induced in that region. These are specific experiments which were investigated on further, and many great minds like Maxwell and Hertz discovered a much more unifying principle that linked the electrical and magnetic phenomena. What they discovered is that a time-changing electrical field will generate a time-changing magnetic field, and a time-changing magnetic field will generate a time-changing electrical field. So in a sense, we can say that these time-changing fields are generating each other. And as a result, we realize that if these phenomena are changing with time, if the electrical field or the magnetic field is changing with time, one will not exist without the other. You cannot have a time-changing electrical field without a time-changing magnetic field accompanying it, and vice versa. So this is not an electrical phenomenon, this is not a magnetic phenomenon, this is an electromagnetic phenomenon, which we now understand to be electromagnetic waves. So let's delve into this a little deeper. Let's think about a charge sitting in space. So here we have a charge. We know that any positive charge has lines of force radiating from it, and they are oriented in the outward direction. Conversely, we also know that if we are dealing with a negative charge, it too has lines of force, which we call electrical field lines, and these point towards the charge. So with respect to us, if we are encountering a stationary charge, we will feel a static electrical field depending on our distance from the charge, which is not changing with time. Now let's change the situation a little. Let's say we are dealing with a charge which is moving through space at a constant velocity with respect to us. So we have a charge here, and this charge has a velocity, let's call it v, and it is moving at a constant velocity with respect to you, the observer. What will you feel, or what will you perceive? You will perceive that this moving charge is generating a magnetic field. So this charge will be generating some kind of a magnetic influence around it in closed loops, in opposition to electrical fields which are not circulatory. These fields caused by charges moving at constant velocity are closed loops or closed lines of force, and these are what we call magnetic field lines. So a stationary charge is generating an electrical field, while a moving charge is generating a magnetic field. Now, what happens when a charge begins to oscillate? So, if a charge is oscillating in space, which means that it is moving rapidly to and fro, it can be in any orientation. So, it is moving rapidly to and fro. What will we observe? In that case, from our perspective, the electrical field that we are perceiving will change because the distance of the charge from us is changing with time. And due to the fact that the electrical field is changing with time, there will also be a magnetic field which is changing with time. So we will perceive a wave being emitted by this charge, and that wave will contain both an electrical and a magnetic component. It will be an electromagnetic wave. Because this charge, which is oscillating, is generating the electromagnetic wave, the energy of the charge will reduce because electromagnetic waves carry energy with them. Let's understand this in more detail with some mathematical equations. So for an oscillating charge or for an accelerating charge, there will be an electromagnetic wave. This wave will contain an electrical component and a magnetic component, and these two components are defined by a set of equations. So we can say that the electrical component Ex is equal to E naught sine kz minus omega t. Now let's explore this equation. E naught is the peak value of electrical field in this electromagnetic wave, the maximum value it can reach. Sine is obviously the sign ratio. K is called the propagation vector. This is known as the propagation vector. Here we are dealing only with the magnitude of the vector, not the direction. But the direction of the propagation vector tells us the direction in which the actual wave is traveling. Omega is known as the cyclic frequency for this wave, which is measured in radians per second, and t is time. You will also notice that electrical field is defined for the x-axis, while the propagation direction is defined for the z-axis. This tells us that the direction in which the electrical field is varying is not the same as the direction in which it is moving. These two directions are mutually perpendicular. One is defined along the x-axis, the other is defined along the z-axis. Moving on, let's look at the magnetic component of this field. So we can write the magnetic component as By is equal to B naught sine kz minus omega t. Let's look at this equation. First of all, we see that B is defined for the y-axis, so it is not on the same axis as the electrical field. It is on an axis which is perpendicular to the electrical field. This means that in the electromagnetic wave, the direction of the electrical field and the direction of the magnetic field will be perpendicular to each other. They are on two orthogonal or perpendicular axes. Another thing that we notice is that the argument for the sine function in both cases are exactly the same. In other words, there is no phase difference between these two waves. The electrical and magnetic wave fields are varying together in synchronization. They are reaching their peak value at the same time, they're reaching zero value at the same time, they're reaching negative values at the same time. And in both cases, the propagation vector is defined for the z-axis. This means that both the electrical and the magnetic field are progressing in the z direction. We can visualize this wave using a 3D graph. So let's set up a 3D system. So here is our x-axis, here is our y-axis, and this is our z-axis. And we have the electrical field. So the electrical field is varying with time. So this is the electrical field. The electrical field's value is changing. So it is reaching a peak value. So this is the peak value denoted by E naught. It again reaches zero. Then it goes to its negative peak value here in the trough, and the cycle keeps on repeating. In the same way, we have the magnetic field. Now the magnetic field is aligned on a different axis. So here is the magnetic field. We notice that in this case, the magnetic field is aligned towards the y-axis. So again, it is reaching a peak value, it is reaching zero, and then it is going to a trough value. And we also observe that both of these waves are propagating not in the x direction, not in the y direction, but in the z direction. So these two waves, the electrical field and the magnetic field waves, are perpendicular not only to each other, but also to the direction in which they are propagating. What else can we learn from this equation? The propagation vector here, which is denoted by k, is equal to 2 pi by lambda in magnitude, where lambda is the wavelength of the wave. Wavelength of the wave. The speed of this wave, the speed at which the disturbance propagates through space, is given by the formula omega upon k. Now, we can define the speed of the electromagnetic wave using the symbol small c. So, small c is equal to omega upon k. Or, in other words, we can say that omega is equal to ck. You are probably not very familiar with this particular equation. So, here is a more familiar form. Omega is the cyclic frequency of this wave. Omega can also be written as 2 pi f, where f is the Hertz frequency. Remember, we measure omega using radians per second. We measure f in Hertz. So omega is also equal to 2 pi f. So we can say 2 pi f is equal to Ck. Now we already know that k is equal to 2 pi by lambda. So we can say, using these two equations, we can say that 2 pi f is equal to c 2 pi by lambda. So we can cancel out the like terms. That gives us f is equal to c upon lambda. Now frequency is not usually denoted with f. It's denoted using a letter of the Greek alphabet, which is pronounced as nu. So this is not a v. This is not a v. This is pronounced nu. So nu is the symbol that we use as a standard for frequency in physics. So this tells us that we have nu is equal to c upon lambda, or we can say that nu multiplied by lambda will give us c, c being the speed of the wave. This is the form of the equation that you are more familiar with. Now, if we were to calculate the value of c using the properties of electrical and magnetic fields, which are beyond the scope of this particular session, we would come to the answer that c is equal to 1 upon mu naught and epsilon naught under root, where mu naught is the permeability, the magnetic permeability of free space, and epsilon naught is the electrical permittivity of free space. And if you were to calculate the value of c based on these parameters, you would find that this value is suspiciously close to the speed of light in a vacuum. This provided Maxwell with a very important clue that light is not some separate phenomena, it is simply a form of electromagnetic wave. And in fact, as he further investigated this phenomenon, he realized that light can undergo polarization, light can undergo diffraction, light can undergo interference, just as would be expected from any wave phenomenon. So this told us that light is actually a type of electromagnetic wave. And in free space, light travels at the speed of c equal to 1 upon root mu naught times epsilon naught. But that raises a question. If free space has electrical and magnetic properties, what happens when light is traveling through a physical medium? For example, what happens when light is traveling through water or light is traveling through glass? Well, let's say that we have a medium capital M, and this medium has its own permittivity, that is epsilon, and its own permeability, that is mu. In this particular case, the speed of light in this medium will be equal to 1 upon root mu epsilon naught, and this has been experimentally verified thousands of times by now, and that tells us that light really is a type of electromagnetic wave. This light contains energy, and we can define this energy in the form of energy density per square meter. For example, if we have an electromagnetic wave propagating through space, so here we have an electromagnetic wave propagating through space, and this is the direction of propagation. We can define a unit area. So this is our unit area in such a way that this area is perpendicular to the direction of propagation. So we can define what is the energy density of the wave in this region, or in other words, how much energy is being transferred through a given unit area of space. The energy density of this wave due to its electrical field, so the energy density due to the electrical field in this region is given as epsilon naught E square by 2, where E square is the square of the strength of the electrical field, epsilon naught is the permittivity of free space, And the energy density due to the magnetic field in that same region can be measured as b square upon 2 mu naught, where b square is the square of the strength of the magnetic field in that region of space. So an electromagnetic wave can travel through free space. In other words, it does not require any physical medium. It will undergo diffraction, interference, all the phenomena that you would expect from a wave phenomenon are present here. We also realize that it carries energy with it through a given region of space. In addition to all this, we also realize that all the phenomena that we thought were separate, for example, microwaves, the light because of which you are able to see this video, gamma rays that come from space, X-rays that are used to check your hand for fractures, all of them are simply various types of electromagnetic waves. These are all the same phenomenon, not even similar phenomenon, they are the same phenomenon. Another interesting question is, can an electromagnetic wave transfer momentum or carry momentum? Because an EM wave has no mass. So logically, we would think that it will also have no momentum. This is not really true. The reason for this is, as the EM wave is traveling through space, let's say an EM wave is traveling through space, as it transits through a given region, through a given area, if that surface absorbs this EM energy, there will be a change in the momentum of that surface. So we can say that an EM wave not only has energy, it also has a momentum. And the amount of momentum that is transferred to a given surface, let's say the total energy of the wave is U. The amount of momentum transferred to a given surface which is capturing this energy U is given as P, that is the momentum, is equal to U, that is the total energy of the wave, divided by C. So we realize a very strange result, that even though an EM wave has no mass, it is still able to transfer momentum, it still has a momentum. In fact, there is an invention, a very ingenious invention called a solar sail. A solar sail is just a very large, very thin and delicate membrane made of reflective material. And when light from our sun strikes this material, the photons carry energy and they transfer momentum to this material. So you can easily fix a space probe to the sail, and the pressure of the light impacting on the sail will cause the sail to move. And this is free energy you are getting from the sun. So you can achieve some insane speeds. There are ideas, there are project ideas where a spacecraft can reach over 100 kilometers per second using this principle of momentum transferred from an electromagnetic wave.
Manorama Horizon. Learning made simple.